In February 2021, fragments of a rare kind of meteorite were found on a driveway in Gloucestershire. It became known as the Winchcombe meteorite, and since that time scientists have been studying it to learn more about its makeup, its history, and what this can tell us about the formation of our planet and solar system. Dr. Luke Daly is part of a team that has been studying the meteorite over the past few years. We spoke to him to find out more about a recent discovery that's revealing just how rare and special this space rock really is.
So hi, thanks very much for having me. My name's Dr. Luke Daly. I'm a reader in planetary geoscience in the School of Geographical and Earth Sciences at the University of Glasgow.
Well, thanks very much for coming on the podcast, Luke, and for talking to us today. And we're going to be talking today about the Winchcombe meteorite, which it feels like a long time ago. And I was thinking about this, and I think it's probably because we were in the midst of the pandemic when it all happened. It feels like a lifetime ago. It's hard to believe it was only 3 years ago, isn't it?
Yeah, absolutely. Yeah. This thing blazed through our skies on the 28th of February, 2021. 12 hours later, the Wilcox family found a piece of it on their driveway. And then 6 days later, me and the team were lucky enough to be wandering up and down a sheep field. And the beady eyes of my partner, Mira Ihaz, and her diligent sweeping the ground, ruling out all the sheep poo that look weirdly like meteorites on the ground, spotted the piece that is now on display at the Natural History Museum in London, which is, like it feels like a lifetime ago. I feel like I've been studying this thing most of my career, but it's amazing to think it's only been 3 years since we've had this really special stone.
Absolutely. What was it like on the day? Did you hear about it from the breaking news, or did a colleague ring you? How did you hear about it?
So I think I first heard about it from Twitter and social media just kind of blowing up, because this thing was really bright. This fireball that blazed across the UK skies was seen as far north, Scotland, seen in France, over into Scandinavia, across into Ireland. So there was a big kind of storm about this really cool event. People's doorbell cameras had captured it. And so I also run one of the networks within the UK Fireball Alliance, a network called the UK Fireball Network, which is a big collaboration with my colleagues and friends over in Australia. It's this worldwide network called the Global Fireball Observatory. And, we've had like false alarms, near misses in the past. So I just pinged an email off to my colleagues over in Australia saying, hey, look, this big bright fireball. I think our cameras might have caught it as well. Any chance this one dropped a meteorite? And then I went to bed, which was probably a mistake, because I woke up like 7 o'clock the next morning to a barrage of the most excited, awesome emails I'd ever heard of, like, oh my God, there's definitely a meteorite landed here. Its orbit seems really interesting. Yeah. How do we go get it in the middle of a national lockdown when we're not allowed to leave our houses?
So you live and work in Glasgow. So how quickly were you able to make the journey, and how did you get down there while adhering to the restrictions?
Yeah, well, I guess first things first, what we did was go, right, we don't know, we know there's a rock on the ground somewhere. It's going to take some time to get institutional level sign off on this. So and we also don't want to encourage people to like flaunt lockdown regulations and sort of swamp the Cotswolds looking for little black rocks. So what we did is I got on the radio, colleagues at the UK Meteor Observation Network and the Natural History Museum got on the telly and said, hey, look, if you're in and around Cheltenham, Winchcombe area, on your daily allowed wander outside your house, and you happen to see a new rock that wasn't there yesterday and looks a bit different to anything you might be expecting, send us a picture. And then sort of like the next day, we kind of got this kind of rogues gallery of amazing images of people who'd sent pictures of their little black rocks that they'd found. And hiding in and amongst those was this unassuming pile of black dust, which looked for all the world like someone had pranked us and thrown a lump of coal on someone's driveway. But also turns out that's exactly what happens when a very rare type of meteorite slams down into a driveway and shatters into a million pieces. And so once we'd got a team out to check that, as one of our colleagues, Richard Greenwood, lived in the local area, so could get there safely to sort of like meet socially distance with the people who found it, the Wilcock family, and confirmed that it was in fact a meteorite. And we knew that there would be more fragments there. That's when we started to go, okay, this hasn't happened for 30 years. It's a really rare type of meteorite. I think this is now justification for extenuating circumstances. Let's try and get a search team to find the rest of it. And then it was a literal mountain of paperwork to get institutional level sign-off, risk assessments. It went all the way up to like the top of the university management chain to get this thing signed off. And there was very, very strict rules about what we could and couldn't do. And because of those strict rules, we had to go in individual cars, and we were only allowed 4 people. And so that's why my partner Mira ended up on the trip, because we were one household. We could go down together, and that was one extra person we could bring with us. And she very kindly volunteered her time. She's not an academic, she doesn't work at universities. She's got a real job working in the space sector, sort of recruiting for satellite companies. And so I was working from the hotel room for most of the time when we were searching. And in fact, the one day she came on the search, that's when we found the piece.
Amazing. So why was this so exciting in terms of the whole space rocks arena? Why do we study space rocks? Why do we study meteorites? What can they tell us?
So I guess it kind of goes back to some of the biggest questions we have as a species. Like, why are we here? How did we come to be? And these are the kind of questions planetary science is trying to address. It's trying to address, how do you form a solar system? How do you form planets? How do you form planets in habitable regions of that solar system and provide them with the opportunity for life to emerge on them, like the Earth? And is that common in our galaxy, in our universe? Should there be life elsewhere? Are we alone in the universe? And basically, by studying meteorites, particularly primitive meteorites, like the Winchcombe meteorite, these are the building blocks of everything else. They're kind of like the Lego bricks that build up the terrestrial planets, moons, asteroids, planetesimals. And so by studying them, we can figure out what the solar system used to be like and the different reservoirs of material that could come together to build worlds that have the opportunity for life to emerge on them, like the Earth.
Incredible. How do you actually go about doing that? And perhaps, maybe we should specifically focus on the Winchcombe meteorite. So once you get the sample, what then happens?
Well, I guess maybe like one of the reasons the Winchcombe meteorite is so special, let's take a step back, is most meteorites are just fortuitous finds. We send expeditions to Antarctica, the Australian outback, the Sahara Desert, and you wander along and you find little black rocks that are from space. But we don't know when they landed, we don't know where they're from. We've built this network of cameras that observe the fireball come through our atmosphere, which not only figures out that a meteorite fell out of the light at the end, but where it landed and also its orbit, where it came from in space, to give that vital contextual information. And we only have that for about 50 rocks out of the 60,000 rocks in worldwide collections. So it's a very special stone to have that geological context embedded in the data set. Then once we've got that rock, what was amazing about the Winchcombe meteorite is this is the first time this has happened in the UK for 30 years, the first time a meteorite's been seen to fall and then recovered. Everyone got very, very excited about it. And literally every lab, it feels like in the UK, turned on all their machines, and bits of the Winchcombe meteorite were sent to each lab to study with their speciality. So we have looked at this thing in intimate detail, from using techniques such as X-ray computed tomography, which is basically like you put yourself in an X-ray scanner. Instead of scanning your bones, as you would if you had like a broken arm or something, we're scanning the meteorite to figure out what objects and grains and minerals and materials are inside it. Then we cut it up, polish it down, and put it in a whole suite of other fancy instruments like electron microscopes, which literally fire lightning at the sample, and interactions with that basically beam of electrons or lightning bolt. We can figure out what its chemistry is, what its crystallography is, and image it and see what this thing looks like at the micrometer scale. We can shoot it with all sorts of lasers to figure out not only what elements are in there, but what isotopes of those elements are in there. So an isotope is just the same element with a different number of neutrons. So it's the same properties, just a bit heavier or lighter. We've looked using transmission electron microscopy at that's getting towards the atomic scale. And then finally, atom probe tomography, which is one of my favorite techniques, where you literally measure one atom at a time and reconstruct this kind of 3D atom cloud at the nanoscale. So normally this kind of depth of analysis is reserved for a $1 billion space mission where NASA or the Japanese Space Agency have sent a probe to an asteroid and brought back a few grams. It's kind of unprecedented that this level of analysis has been undertaken on a meteorite fall, but just kind of shows you how interesting, rare, and excited the UK and international community has been with this stone. And it's still continuing to tell us some really interesting stories about how our solar system formed and maybe how water was delivered to the early Earth.
That's incredible. Yeah, I did hear quite a lot of sort of mention of the speed with which it was recovered. So does that mean that it was less contaminated? It's a pure sample. And is that, do you think, why it was given so much scientific attention and it was allowed those sorts of experiments and testing?
Absolutely. So the Winchcombe meteorite is a type of meteorite called a CM carbonaceous chondrite, which is a very rare type, and it's also the front runner candidate for delivery of water to the early Earth and organic material to the early Earth. Basically, all the building blocks you want to seed a young planet with for it to have all the ingredients for life to emerge on it. The slight wrinkle has been because it's so water rich, all the original minerals in it have turned into clay, and clay is really rubbish at holding on to anything and very quickly reacts with Earth's oxidizing environment. So one of the kind of questions has been, does it look like the Earth in terms of its water, because all these meteorites have been sitting on the Earth for 1,000 years and it's very nicely equilibrated, so it looks like Earth's oceans because it's exchanged its water with the Earth? Or is it the delivery mechanism? And because we got Winchcombe so quickly, particularly the stones that were recovered from the Wilcox driveway, they were recovered within 12 hours. There was no rainfall or anything. So short of literally going to an asteroid with a space probe, landing on it and bringing that material back, that's as good as you can get. And so when we've looked at the water content in the Winchcombe meteorite, it is a very, very close match to Earth's ocean. So it's a kind of very solid piece of evidence that these carbonaceous type asteroids and carbonaceous type meteorites might have been the prime delivery mechanism for water and organic material to the early Earth.
It's absolutely incredible. I mean, you're saying, it was sort of recovered within 12 hours, which when you can compare that to 4 billion years, I mean, 12 hours is...
Yeah, absolutely. Yeah, compared to its storied history of 4.5 billion years, it's literally the blink of an eye. But as we kind of shown, that blink of an eye can be incredibly important. So a different study that was published by one of our PhD students, Laura Jenkins, looked at the stone that we recovered, Mira found in the field. And even after those kind of 5-6 days that had been there, again, no rainfall, no anything, just sitting in a sheep field, certain minerals had started to change and new minerals had started to grow within it. So you need to get it that quickly. Otherwise, it very quickly starts to degrade, starts to change, and starts to equilibrate with Earth's atmosphere. So it's so important that we get these things really quick.
Wasn't there a discovery with part of the paper that came out about its origin being like a jigsaw puzzle? It'd been falling apart and come back together again. How does that work?
So yeah. So that was this is a kind of really interesting phenomena of CM meteorites. Is a lot of them are what we call breccias, and a breccia is just basically a lot of rocks in the same rock that have all been welded together. They're all the same type, so they're all CM clasts of a CM meteorite, but they're texturally different, chemically different, crystallographically different to each other. So you can see they've had different geological histories. And that's been well established for CM meteorites. It's really interesting that the Winchcombe meteorite, Martin Suttle wrote a paper that showed there are like 8 different lithologies, so 8 different types of CM meteorite in this one meteorite. And the team that I was leading and the paper that just came out has been looking at those individual lithologies in even more detail. And what we were seeing is we kind of expect each individual class, each individual rock within that breccia to have its own geological history. And so it saw all the same things, saw the same response to the fluids going through that asteroid, altered to the same extent, etc. What we saw basically wasn't that. What we saw was grains that have been completely altered by fluids, completely wrecked. They're now clays, secondary minerals, sitting right next to, within the like breadth of a human hair, next to grains of the same mineral that's completely pristine, untouched. That if any fluid went anywhere near it, you're talking about a day, it would be clay. And so you go, okay, how does that survive right next to this thing that is completely changed by fluids? But it's not just at the kind of human hair scale, it goes all the way down to the atomic scale. So we saw this amorphous glass grain sitting right next to these beautiful fibers of clay. And glass, when you expose it to fluids in the asteroidal environment, changes to clay almost immediately. And so you're thinking, well, okay, how does this thing survive? It's sitting like a nanometer away from complete clay assemblage. And so we think of these Winchcombe meteorites and the CM meteorites as a breccia, which is kind of like a jigsaw puzzle. You've got lots of different pieces of that puzzle all put together. What we were kind of seeing is actually each individual grain and each individual component within those rocks also has its own unique geological history. And so it's like you've taken those pieces of the jigsaw puzzle, cut them all up together, jumbled them all together as well. And so what's happening is essentially you're forming an asteroid, altering it by fluids, breaking it apart at the nanoscale and at the grain scale, reassembling it, breaking it apart again and reassembling it. And so you eventually have this kind of jumble rubble pile asteroid, which has been completely disrupted and reaccreted at multiple scales over and over and over again. So this poor rock's seen some things. It's been through a really tough time.
So, I mean, you can sort of like detective work. You can work out the story of what's happened to this meteorite. How could it split apart and come back together again, though?
So there are a number of ways you can do this. The early solar system is a very violent, turbulent environment. One of the kind of, I guess, easiest ways to do this is throw another asteroid of a similar size at it very quickly. That basically shatters it into a million pieces. However, that doesn't necessarily break it apart at the grain scale. It can, absolutely. If it's very loosely bound together, you'll just shatter it. And that's fine. Another way people have proposed you can do it is when we think these things initially come together, they're these like 90% porous candy floss-like objects that are basically loosely bound by static and not a lot else. Once you start melting the ice and gas and sort of like solid, like carbon dioxide, solid water, within that candy floss-like structure, it expands and could basically blow and destroy and detonate that whole object. And then it has to start again and recompile. What's kind of nice about this as well is when we're trying to think about these things as building blocks, it'd be really lovely to know what they were before. Because we have this disaggregation, reaccretion, we find objects that we aren't expecting to survive because they're very susceptible to fluids within these very altered meteorites. And so we can start to figure out what their original mineralogy, what the original components of these things could have been.
That's incredible. And do you sort of, so with something like this, with the Winchcombe meteorite, and then as you were talking about the sample collection missions like OSIRIS-REx, presumably within those missions there is, comparison, and you can build up a bigger picture of the early solar system, and you can use all these different samples over time. I was just wondering about what's the sort of collaboration between different papers and different studies and different scientists, and how does it all mingle to create a whole narrative?
Yeah, absolutely. So a lot of the people that were involved in this study and that have been studying the Winchcombe meteorite are world experts in the study of carbonaceous asteroids. So, for example, I'm on the Hayabusa 2 mission that went to sample the asteroid Ryugu, and we've been looking at those materials and sort of contributing to those studies. A few other folks, sadly not me yet, but working on the OSIRIS-REx mission, looking at the material from Bennu. And there are absolute comparisons and lessons to be learned from the study of both of those things. Both of those asteroids. One of the potential implications as well is going back to what these asteroids were made of originally. In the Winchcombe meteorite, because we had this kind of preservation of alteration extent, we noticed there's this really interesting texture, which we call a pseudomorph texture. Basically, the secondary new mineral that's replacing the primary mineral is the exact same shape and the exact same kind of texture as the mineral it's replacing. And CM meteorites have this really interesting mineral assemblage that's like classically in the CMs called tachylonite cronstite intergrowths, or TCIs. And we noticed that they have the exact same texture as carbonate grains within this rock. And in fact, we see this kind of preferential kind of complete alteration sequence where you've got perfect pristine carbonate and then carbonate surrounded by a TCI as it's eating its way in, and then a complete TCI with the exact same crystallography as the original carbonate. This raised a really uncomfortable kind of conclusion when we were writing this paper, that these rocks should be maybe 20 to 40% more carbon rich than we think they are, which is a huge amount. And one of the key questions is, where did it come from and where did it go? And where did it go might be answered by NASA's observations at the asteroid Bennu, where they've seen these beautiful carbonate veins, which we don't see in meteorites, probably because they get destroyed as that thing comes through Earth's atmosphere. But these really lovely carbonate veins streaking across the asteroid. And so you can imagine as you dissolve those carbonates, they move into the fluid and get injected and precipitated along these vein-like structures. So that could be an explanation for where that carbon has since gone after it was replaced by these TCI-like objects in the Winchcombe meteorite.
I can imagine that must be really, really, really satisfying whenever the sort of things fall into place, and you can solve a piece of the puzzle through that. Whenever I sort of speak to someone like yourself, and we're talking about space rocks and meteorites and asteroids and comets, it does just feel like just planet Earth wouldn't be what it is today. We wouldn't have life. We wouldn't have water without. Is that the sort of picture that you think we're sort of building up over time?
I think in some ways, yes. From the more we learn about how we think planets form, how our solar system came to be, there's this kind of presiding idea that Earth should have formed dry. And there's kind of two main reasons for that. One, where Earth formed is in the inner solar system, relatively close to the sun. That region of the gas disk is relatively hot. Any water or organic material are in the vapor phase and they get blown out into the outer solar system and you lose them. Secondly, any water that you do manage to somehow infuse into the early Earth gets immediately lost when something the size of Mars smashes into us to form the moon, completely melting and degassing the entire mantle and blowing off the atmosphere. And so on every account, Earth should be a bone-dry desert world. And I mean, I live in Glasgow. It rains here all the time. I think it's been raining here relentlessly since about January. So that's clearly changed since 4.5 billion years ago. And what we kind of think has happened is these water-rich asteroids from the outer solar system get destabilized. And out there, of course, there is all the water in ice form, so it's able to go into those early formed bodies in the outer solar system. They get slung into the inner solar system, turn the inner solar system into a pinball machine, bringing with it abundant water and abundant organic material to seed those terrestrial planets with water, with all the ingredients basically they need for life. So on one side, you can see that's very lucky that the Earth got its water this way. It should be a desert world. But every solar system in our galaxy should have water-rich asteroids in its outer reaches. And if those get destabilized through any number of mechanisms, water should be delivered to the terrestrial planets across our galaxy, across our universe. So that shouldn't be an uncommon mechanism. So it might not be whether planets get seeded with all the right ingredients, it's whether they hang on to them for long enough for life to get going on the surface.
Just to sort of close, presumably more work is going to be done on the Winchcombe meteorite. Do you have more sort of studying time? What are your sort of future investigations?
Absolutely. I think the Winchcombe meteorite is essentially the gift that keeps on giving. And while I like to kind of highlight, this is a huge amount of work. Hundreds of people have put in thousands of hours over the last 3 years to study the stone. That's the kind of power of doing this kind of big data approach, of throwing everything at it, studying it from lots of different perspectives, and that diversity of opinion, diversity of viewpoints, diversity of techniques brings these really interesting observations. But there is still more to be done. There is so much more material that we haven't looked at yet. For example, I have a master's student working with me right now called Heather Gibson, who is doing a phenomenal job looking at some of the material from some of the other fall sites that hasn't been studied in any detail at all. And there's some really interesting results that they're getting from those studies. But I'll save that to let her tell that story when the time is right. But yeah, still absolutely loads more to do. Like you said, linking it to space missions, future space missions, OSIRIS-REx, Hayabusa 2, and other materials we're bringing back from asteroids, as well as comparing it to potentially future meteorite falls. I'm very hopeful we should get another meteorite in the UK, particularly now we've got all these cameras and we know the system works. It's just a matter of time before we get the next one, and then everyone turns on all their machines again and we study that stone. So still lots of questions to answer, and still lots of insights that the Winchcombe meteorite can give us going forward, even though it's already given us so much. Yeah,
it's amazing what can happen in 3 years, isn't it?
Yeah, it's incredible. How to put this? I didn't expect this to happen. I expected we'd eventually get a meteorite from the Fireball Alliance and the Fireball networks. I didn't expect it to be this awesome first time round, that it's a rare stone, tells us so much about Earth's origins, our origins. It's a very, very special piece, and very privileged to be part of the team, able to study this really interesting rock.
Fantastic. Will you keep in touch with us then, and let us know anything else? Any future?
100%. Yeah. Always love sharing these awesome stories. Always happy to come on the show.
Fantastic. Well, thanks for coming on, Luke, and I hope we speak to you again soon then.
Thanks so much. Cheers.
Cheers.